Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Today we continue our class about the electronic circuits one, and today we will discuss about the common base configuration after we already discussed in last week about the common collector and also common emitter. Okay, and what is the common base configuration? Please look at the picture we see here in this picture. This is the common base. The base is connected to the ground. This is the ground, negative. This is the ground. Okay, and then the input is coming to the emitter, the emitter terminal here, and then this output we look at the collector terminal. And then the characteristic of this common base configuration is a little bit different with the common emitter and common collector. We see that the common emitter and common collector has high input impedance, but for the common base configuration, because of in common base configuration, we connect the emitter with the ground, so it will connected parallel with the small emitter resistor here. So we have the parallel connection between the emitter resistor RE, big RE, and small RE emitter resistor. So because of the big RE parallel with the small RE, so it will be similar to the small RE. So this is the low impedance. So this is the characteristic of the common base. And then we see here that the collector resistor is connected parallel also with the collector terminal and the ground. So the output impedance is determined by the collector resistor, and so the characteristic of common base is high output impedance is different with the common collector or emitter follower we talked in last week, because of in common emitter the characteristic of the common collector is low output impedance, and then the current gain is less than unity, and then we have the very high voltage gain here, and there is no phase shift between the input and the output, and is similar to the common collector or emitter follower for the no phase shift. And why this common base configuration has current gain less than unity and then very high voltage gain, we will discuss later. Okay, so the input impedance, as I talked before, is the parallel between the emitter resistor and then small RE, and then its output impedance is determined by collector resistor RC, and then the voltage gain AV is VO per VI. VO is output voltage and VI is input voltage, and then here the VO is alpha RC here, and then VI is RE. So alpha is similar to 1, the alpha is similar to 1, so we can neglect the alpha. So the AV is RC per RE, and then the current gain AI is EO per IE is minus alpha is minus 1. So so the current gain is only affected by the value of the alpha, and then maximum alpha is 1. Okay, and then for this network, determine this RE, ZI, ZO, FV, and AI. And then the first one, how to determine RE. So we have to, the RE is 26 millivolt per IA. So um, we have to determine the IE here, IE. Okay, IE here. So IE is VEE minus VBE per RE in DC analysis. Okay, so in this loop, this is the VEE. Okay, so we got that 2, VE is 2, VBE is minus 0.7 per 1 kilo ohm. We got that 1.3 milliampere. So the small RE is 20 millivolt per 1.3 milliampere. We got that IE is 20 ohm. And then ZI is RE per small RE. RE is 1 kilo ohm and small RE is 20 ohm. We got that ZI is a little bit similar to RE is 19.61 ohm. So this is the low impedance characteristic. And then ZO is equal to RC. RC is 5 kilo ohm, so the ZO is 5 kilo ohm, and AV is RC per RE, as RC is 5 kilo ohm, and small RE is 20 ohm. We got that 250, and IE is minus alpha, and we got that alpha is 0.98, so we got that AI is minus 0.98 or similar to minus 1. And then the last one is the common emitter collector feedback. So we connected RF here as a feedback between the collector terminal to the base terminal. This is the collector terminal and this is the base terminal. And we didn't connect any input bias in the base terminal. Okay, so this is the variation of the common emitter fixed bias. In fixed bias, we connected the base resistor to the bias voltage. But here we connected this is the feedback resistor to the collector terminal. And then the input is applied to the base, and then output is taken from the collector. And then there is a 180 phase shift between the input and the output. So if we draw in the RE model, it's become like this one. This is the base for the input, and then we have the beta RE for the input impedance, and then we have the feedback resistor between the base terminal and the collector terminal. And then in the collector terminal, we have the beta IB, and then the output, we have the collector resistor here. Okay, so for the input impedance here, so for input impedance is determined not only beta RE, but we have the feedback resistor. So the input impedance is become RE small RE per 1 per beta plus RC per RF. And then the output impedance is determined by RC parallel to RF. And then voltage gain AV is VO per VI is minus RC per RE. And then the current gain is IO per IE is beta RF per RF plus beta RC, or AI is IO per IE is RF per RC. So the current gain is determined by the feedback resistor, but for voltage gain is determined by the collector resistor and then small RE. For output impedance and also input impedance is determined by the feedback resistor. So for this network, determine this parameter. Okay, so the first one we have to calculate the RE, so we have to calculate the IE here. So for IE, VCC minus VBE per RF plus beta RC. Okay, we already discussed this in DC analysis for the feedback. So we got that IB is 11.53 microampere. And then IE is beta plus 1 IB, as we know this equation. So we got that IE is 2.32 milliampere. So the RE, small RE is 26 millivolt per IE, is we got that 11.21 ohm. So input impedance using this equation, we got that RE plus per 1 per beta plus RC per RF, and then we got this parameter. We got that the I is 560.5 ohm, and then ZO is RC parallel to RF. We got that ZO is 2.666 kilo ohm, and AV is minus RC per RE. We got that AV is minus 240.86. And actually, you can please read to the book how to got this equation. I mean that the input impedance, the output impedance, voltage gain, and current gain to to get the full understanding about this chapter. Okay, and then repeat if the RO is 20 kilo ohm. So repeat, we have the condition RO is not satisfied, so we have to calculate ZI using if in this analysis, and then also the ZO, AV, and okay, I think this is the enough for this common collector feedback configurations. And thank you very much for your attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.